Welcome to the physics class for January the 5th. A couple announcements as usual before we start into today's material. So first off, hang on, somebody just arrived here. Let me let them into the class. Okay. All right. Mark him tardy. Okay. So a couple announcements. First off, we will be finishing up chapter 11 today. So in theory, we could take the test next time we meet, but I'm sure that you guys would approve or would prefer to have a review day. So that's what we'll do. Therefore, the test will be first time we meet next week. Make sure that you get all your quizzes done. If you haven't done all the quizzes, do that. They've all been unlocked now, except for the one that's due today. I need a little bit of time to look that one over, but then later today I'll unlock that one. Also, make sure you get in any late homework. Once the test has been given, then no more quiz retakes, no more late homeworks allowed. The focus for the test is going to be on chapters 9 through 11, but as usual, you need to know everything that we've learned all year long. You need to know all the equations of motion and all the basic definitions and things. So, I mean, every test we give in cumulative or in physics is always a cumulative test, even though the emphasis is on the newer stuff. Now, there is a practice test online, and maybe it's worth taking a quick look at that. So let me go here. That's the homework for tonight. We'll get back to that in just a second. Okay, so if you look on Canvas, then you will find, let's see, come on, hurry up. There we go. All right, so you'll see, here's tonight's homework. There is not a quiz. I'm not going to give you a quiz for tonight. I don't like to give quizzes that close to the real test. But there is something here that I put on over the break that some of you may have seen, some of you not. This is the practice test. It's up right now, been up for a while. Notice I've got a little note on here that says, don't attempt problem number 19 until we've talked about it. The reason for that is problem number 19 actually uses something that we need to know from chapter 12, which we have not yet talked about. There's just this one little piece of information from chapter 12 that I think is important, and I like to group it together with the test that we're going to take here. We're not going to talk about it today, but next time we meet, which for those of you in the 8A class is on Thursday, I will briefly introduce this one thing from chapter 12, and you will be responsible to know it for the test. It's pretty simple, but we've got other stuff that we need to talk about today. So other than problem 19, you should be able to do all the practice test problems. I've got another file down right here, which is the answers to the practice test. That is available right now. There's nothing to stop you from opening up that one and just going right straight to it, other than the fact that it would not be a wise thing to do. The best way to study for a test is do the practice test, open up the file that does not have the answers in it, give it your best shot to do the problems. And if you look at a problem, you say, okay, well, this is really easy, it's a waste of my time to do it. Well, then don't do it. Skip to the ones that you need to do. And only after doing the problems, then open up the answers and see if you got the right answer, and then not go back and figure it out. So with the practice test, there's nothing due. You don't have to turn anything in. It's just there for your benefit. So you'll see that I do have a placeholder in here for the test. It's just a placeholder right now. There's nothing there. If you were to click on it, it'll tell you that it's locked, but it's there. And then underneath it, you see I've got a placeholder here where after the test is over, if you upload a scan or photograph of your work, then maybe I'll give you partial credit on the 5 pointers, just like I always do. All right, and then here's tonight's homework, but let's not talk about tonight's homework just yet. Let's first talk about the answers to last night's homework. Okay, so Sam, I see your comment about animal abuse. Not quite sure what to think of that. Are you saying that you guys are animals and I'm abusing you? If so, well, hey, I'm all for it. Okay, so here are the answers to, not there, here we go. Here are the answers to last night's homework, at least the ones that you haven't already looked up in the back of the book. As usual, if you could only see one problem worked through, what would that one problem be? Please vote in the chat box. What is the one problem that you would like to see most? You don't need to see any problems? Okay, all right. I'm seeing a couple votes for problem 8. I'm seeing a lot of votes for 8. 8 and 16. Let's get a few more people voting. Another vote for 16. Okay, well, I think we have time. We can do both 8 and 16. All right, so let's go ahead and do that. Problem number 8. That's where we lift something and put it on the table and then slide it. I'm thinking. Oops, it's back here. Okay, yeah, we pick up a box, we put it on the table, we slide it along the table, and then we put it down. In other words, okay, and then we ignore friction. Now, ignoring friction turns out to be really important. Let's go ahead and open up a whiteboard here. All right, so here's the floor, here's the table, here's the box. All right, so let's do this in steps. So the first step is we just pick up the box and we put it on the table. So how much work do we do there? Well, if we do a free body diagram on the box while it's in midair there, then we got mg going down and we've got the force going up, and we lift it up a distance that we're going to call h. And so the work that we do is that force, which turns out to be equal to mg, times that distance, force times distance, and also technically times the cosine of theta, but in this case, we don't need that. All right. And so the force is mg, the distance is h, and you say, hey, wait a minute, mgh, that sounds familiar. That is the formula for potential energy, and that is not a coincidence. Yeah, so when the box gets up here on the table, it now has energy, and that energy is equal to the work that we did in lifting the box up. All right, so there's some energy that we used. Now, we're going to slide the box across the table. If there was friction, then we would have to exert a force and keep pushing all the way across the table there. And so if there was friction, then some work would be done at that step. But the problem says that we can ignore friction. So no work is done. Now some of you are going to say, well, wait a minute, Mr. Hendricks, in order to get the thing moving in the first place, didn't you have to push on it to get it moving? The answer is yes. But once you get it moving, then you don't need to keep pushing. It'll just keep on moving, okay? And then when it gets to the other side, you need to stop it. So you're gonna push in the opposite direction in order to stop it. So that little bit of work that you did at the beginning, you get all that work back when you stop it at the end. So if there's no friction, you don't have to worry about it. No work was done there. Okay, then the only other thing is when we lower it back down to the ground, and do they want us to consider lowering? Yep, they want us to consider lowering it back to the ground. Okay, so when we lower it back down to the ground, we're exerting an upward force, but the thing is moving downward. So we're doing negative work. And so that cancels out the work that we did in order to lift it up. So when we're done, the total work ends up being 0. Even though we did 110 joules of work to get it up on the table, when we lowered it down, you can think of it as we did negative work, which means that if we're clever, we can maybe capture that energy and use it to recharge a battery or something like that. And so the total work that's done ends up being 0. Okay, so Jackson is saying, why isn't there work to push it? So there is work to push it. So here's the tabletop. Here is some object that I'm going to push. Okay. So Jackson, you are right. If this thing is sitting here, when I get it moving, okay, I have to do work to get it moving. And so once it starts moving, it has some kinetic energy. And however much kinetic energy it has, well, that's how much work that I did to get it started. Now, I don't need to keep pushing on it. Once it's moving, I can stop pushing. And so it's just going to continue across the table. So at that point, yes, I have done work to get the thing moving. But once it gets to the other side of the table, now I need to stop it, right? And so what I'm doing to stop it is I'm doing negative work. So all of that kinetic energy that I gave it, I now recapture that energy. And so when I stop it, then I get back all of the energy that I put into it for kinetic energy. So does that make sense? So if I gave it a push and I let it keep on going, if I never stopped it, then you are absolutely right, Jackson, because then I would have to say that, yeah, I did some work to give it kinetic energy. But if I stop it when it gets to the other end, then I recover that work. Okay. Same thing like when I lift it up. Okay. When I lift it up, I'm doing positive work. And then when I lower it down, if I'm clever in how I do it, I can recover that energy. And so that's why the network is 0. Okay, now problem 16. Whoops, I went and closed up my book here. Should have left the book open. Problem number 16. Okay, that's where we got the bike rider. Okay. Now, problem number 16 refers back to problem number 15. So let's talk about that one first. All right. So what we've got here is the level ground, and then here's a hill. And so we got a bike rider here who has a mass m, and the bike is moving with some velocity v, and it's coasting. So that means we are not pedaling. So the bike rider is not adding any energy to the system. I mean, to get it moving in the first place, they did, but we're going to start the clock when the bike is already in motion. And so problem number 15 says, okay, so when it comes to the hill and it starts moving up the hill, again, it's coasting. The bicyclist is not pedaling. What's going to happen is it's going to slow down, and eventually it's going to come to a stop. So we want to know when it comes to the stop, how high is it going to be? Well, hopefully you recognize this is a conservation of energy problem. So before it hit the hill here, all of the energy was kinetic. So 1/2 mv squared. And then when it comes up to, and it comes to a stop here, it no longer has any kinetic energy. Where did that kinetic energy go? Well, it went into potential energy. So however much potential energy we have here, that must be equal to however much kinetic energy we had here, provided the bicyclist is not pedaling. Okay, so potential energy is mgh. So that has to equal 1/2 mv squared. The m's cancel out. We solve for h, So you guys didn't ask about number 15, so I'll trust that you got number 15 right. Now in problem number 16, they're saying, well, this time the bicyclist is pedaling. Okay, so when they get to this same point here, where back in problem number 16, the velocity was 0, this time the velocity is not 0 because this time they are pedaling. As they go up the hill, they're pedaling. And so they don't come to a stop here, they just keep on going. And so they get up to some point here where now they're at a higher point. So they've got more potential energy than they had kinetic before. And their kinetic, and the kinetic energy that they have up here is not 0 anymore. They're still moving. So they've definitely got a lot more energy than they had down here. So where did the energy come from? Did we just break the laws of physics or what? How is it possible that when they get up the hill there, they end up having more energy than they did at the very beginning? Anybody want to unmute yourself and try to answer that one? Oh, come on, somebody knows the answer. What's the thing that's different between problem 15 and problem 16? In problem 16, okay, there we go. Yes, way to go, Miriam. Yes, in problem 16, they're pedaling. Okay, so the bicyclist is doing work. So the bicyclist is adding the energy into the system. So where did that energy come from? Well, if you look at the answer here, okay, so what I said here is that the energy comes from the food that the bicyclist ate that morning. So that food had what we call chemical potential energy. And so as the bicyclist body is digesting the food, they're turning that chemical energy into useful mechanical energy. Now, mechanical energy is a term that I've used a couple times, I think, but let's stop and let's make sure we understand. There are many different types of energy. We've learned about kinetic energy, potential energy, and we've also talked about other things like thermal energy and chemical potential energy and magnetic energy and nuclear energy and all those things. So if we take all these different types of energy and we break them up into different categories, there is a category of energy called mechanical energy. And so both kinetic energy and potential energy fall into this category. Now, what makes these types of energies different from the other types of energies is that these types of energies, it's very, very easy to transfer energy from one form to the other and get it all back without losing any of it. In fact, let's go ahead and let's jump into the material that I wanted to talk about tonight, because this leads into it really well. So today we're going to finish up chapter 11. And here is a great example to illustrate what I was just talking about. And you'll see up at the top there, we talk about mechanical energy. All right, so if you look at the pendulum, that is the best way to understand this. So the ball starts out up here, and you see the ball is up at some height, h, above the ground. And the ball swings, and when it gets down to here, the ball is equal with, now it's not touching the ground because we don't want it to rub. That would mess things up. But it's down at the lowest level here. And maybe I shouldn't call it ground. Let's just call it the lowest level. All right. So so it goes up here, and it comes to a complete stop, turns around and goes back the other way, and then just keeps on going back and forth. So if we look at it right here, when it's at what we call point A, all of the energy is potential, because for a brief instant there, the ball comes to a stop, so it has no kinetic energy. All of its energy is potential. And then when it reaches the bottom here, now it's at the lowest level, so it has no potential energy, but it is in motion, so it has kinetic energy. So at point B here, all of the energy is kinetic, none of it is potential. When it gets to the other side, all of it is potential, none of it is kinetic. The total is the same. This line that you see right here, that's the total. The total energy never changes, but the form changes. So like, let's say when it's right here, it's got some kinetic energy, some potential, but the total is still the same. So these two types of energies, kinetic and potential, they are totally interchangeable. You can take it from kinetic to potential and recover it all back again. So we call that mechanical energy. Now that's not the case with thermal energy. If the ball rubs across the floor, then there's friction, and friction converts the energy into thermal energy. And thermal energy is a different beast. I mean, it's still energy, but it's not mechanical energy, because once the energy gets converted into thermal, you can't get it back. Now, there are some tricks. There's a branch of science and a branch of engineering called thermodynamics. And depending on what you major in college, you might have to take a class in thermodynamics. And that's an entire semester-long class that deals with how do you transform thermal energy into usable mechanical energy. And it turns out that there are some tricks that you can get some of the thermal energy back into mechanical energy, but only some of it. You can't get it all. And even getting some of it is pretty tricky. So I'm not going to go into the details there. Just remember that once energy gets converted into thermal, you cannot get it all back. So we don't call that mechanical energy. Now, there is another type of energy that you can get it all back. And so we're going to call that one, we're going to put that one into the same category where we call it mechanical energy. And that's spring energy. So I looked around to try and find a spring. I couldn't find a spring. So imagine that I've got a spring. So imagine that this here is a spring. It's obviously not, but pretend that it is. Okay. So if I push on it, it compresses. And then when I let go, it comes back out again. All right. So let's say I've got a ball, and this ball is coming along and it's moving. So it's got some kinetic energy. It comes and it hits the spring and it compresses the spring. And then the spring brings it to a stop, so it no longer has kinetic energy. But the spring, the compressed spring, now has what we call elastic energy inside of it. Some people call it spring energy. Okay, so we converted our kinetic energy into elastic potential energy. Well, the spring is pushing on the ball. So what's going to happen is that it's going to push the ball back, and the ball is going to end up going. And so we're going to get back all of our mechanical energy, all of the kinetic energy that we had before. We're going to get it all back afterwards. And so this spring energy here, that's considered to be mechanical energy, because we can take our kinetic energy, put it into here, but we can recover it later. Okay, but thermal energy, no. You're lucky if you can get a little bit of the energy back once you've converted into thermal energy, and even doing that is a trick. But even then, you can only get a little of it back. You can't get it all back. Same thing with other types of energies. So the forms of energy that we put in the category of mechanical energy are kinetic energy, potential energy, and then spring potential energy. Right? All of the rest of the types of energies, we put them in a different category. I like to just call it other. Some people call it lost energy. I don't like that term. It's not lost. We know where it went. It's just in a form where we can't necessarily get it all back. So, okay. Now this leads into a little review problem that I want to do. I'd like all of you to get out your pencils, pens, and get out your calculators. I'm going to do a review problem that actually is going to serve two purposes. One is it gives us an important review that we need, because it's been a long winter break, right? But it also leads us into the next thing that we're going to cover. So let's assume that we have a lump of clay that it's traveling through space, and so we don't have to worry about gravity. It's just outer space there. So it's got a mass, let's call it m1. It's moving with some velocity, let's call it v1. And over here we got another lump of clay that has a mass of m2, and it's moving with some, well, tell you what, let's make it easy, just because I want to keep the math easy. Let's assume it's not moving, right? Let's say that the velocity equals 0, so there. And so if let's actually put numbers on here. Let's say this is a 3 kilogram mass of clay. This one here is a 5 kilogram mass. Let's say that the velocity here is 12 meters per second. Okay, so the two of them are going to crash into each other. And so we know that we can do this a couple ways. If they don't stick together, it is possible to still do it, but let's keep it easy. Let's assume that they do stick together. So the before picture here I've done in black ink. Let me switch over to red ink. And so then the after picture looks like this. Here's the one lump of clay, here's the other lump of clay, and they are now stuck together. And I do that just because it makes the math a whole lot easier. And so I want to know now, what is the velocity of this mangled mass of clay going to be? All right. So this is something we did a couple weeks ago. Every single one of you should be able to do this. I guarantee there will be a problem like this on next week's test. So let's take a minute. Let me just stop and have you guys work this out. I want you to come up with a number, and I want you to type your answer in the chat box, but don't type it in as a public message. Type it in as a private message so that only I will be able to see it. Okay. So you guys got started on there? I'll give you a head start. Oh, the mass of clay 2 is 5 kilograms. My handwriting there is not very good. Is that better? Okay. All right, that should be enough of a head start for you guys. So I'm going to get working on it too. Let's see if you can come up with an answer before I do. Okay, I've got an answer. And I don't see any answers from anybody else. So looks like I won. Provided, of course, my answer is right. I need some answers from you guys. Come on, guys. It hasn't been that long, has it? Come on, somebody needs to have an answer here. Okay, I see an answer. And the answer matches mine, so that's reassuring. But I need to, okay, there's another answer, which also matches mine. Okay. Let's get a couple more. Oh boy, I'm getting worried, guys. This should be an easy problem. Now I realize it's been a couple of weeks. Maybe that's the problem. It's been a couple of weeks. So this is a good review problem. All right, so Jackson, you were the first one to have an answer. Can you unmute yourself and tell us how did you do this?
If I'm being honest, I had to like flip a page back in my notes to remind myself.
That's okay.
It was M1V1, I think it was, yeah, M1V1 plus M2V2 equals, uh, M1V1, or it was like M1 plus, or M1 plus M2 in parentheses, and then times V.
Okay, so hold on for just a second there. Okay, so what he said is correct, but it's not the thing that I would hope to see first. So tell you what, let's pretend that this is a problem on next week's test. Because like I said, I guarantee there will be a problem like this on the test. And let's suppose that it's one of the 5-point problems. And so you want to make sure that even if you get the answer wrong, you at least get partial credit, right? So what should you do in order to guarantee that you get partial credit? Well, the first thing that you should write down is not the equation that Jackson just said. The first thing that you should write down is this right here. You should say sigma p before the crash has to equal sigma p after the crash. That is the first thing that you should write down, because that shows me that you recognize that the way to solve problems like this is by using conservation momentum. So you've just earned 1 point by doing that. So even if you mess up everything else and get everything else wrong, you at least get 1 point just for showing me that you realize that conservation momentum is the way to solve the problem. Okay, now we go to what Jackson said. Okay, so Jackson is saying that the momentum we have before the crash is m1v1 plus m2v2. Now, you might say, well, why do I write that? Because v2 is 0. Yeah, but I like to write it anyway, just to make sure I don't forget something. I mean, as soon as I write it, I'm going to cross it out. But writing it is a nice thing just because it ensures that I don't forget something important. Okay, so then that has to equal after the crash. So Jackson, what is our momentum? What's the equation to calculate our momentum after the crash?
Like, the masses in parentheses.
Okay, the mass is in parentheses, and why are they in parentheses?
Because you factor them out, I believe.
Well, it's because they're stuck together.
Oh yeah,
So
that too.
after the crash, as far as we're concerned, it's just one object. Okay, so we put them in parentheses, and but what we need is momentum. So we have to, momentum is mass times velocity, so that's times v final. Okay, so you have now earned 2 points. Okay, you showed me that you're using conservation momentum, and then you showed me that you were able to correctly identify what momentum is. All right, so at this point, even if you mess up everything else, you've earned yourself 2 out of the 5 possible points. All right, what do we do next? Well, let's do a little bit of algebra. And I highly recommend that you do the algebra using the letters, not the numbers, because it's faster and easier. So we're going to divide everything by m1 plus m2 in parentheses. So that goes away. Have to do the same thing to the left side. Okay. So now you've earned yourself 3 points. Okay. Even if you mess up everything else, you've now earned 3 out of the 5 possible points. Okay. So at this point, the algebra is done. So we know the V final is equal to this. All right. Next thing we do is we put in the numbers. So we know what M1 is, we know what V1 is, we know what M1 also goes there and M2 goes there. Okay, so we put in the numbers and actually go ahead and write them in there. Okay, so we're going to write that in as 3 times 12 divided by 3 plus 5. And we should put that in parentheses too, because you got to be careful. If you leave out the parentheses and when you put it into the calculator, you're going to mess yourself up. Okay, so you've now earned yourself 4 out of the 5 possible points. And so let's suppose that we forget about the parentheses and so we mess up when we put it in the calculator. We type 3 times 12 divided by 3 plus 5. Okay, so we're going to get the wrong answer because we didn't put parentheses. Well, hey, that's okay. I'll still give you 4 out of the 5 points, right? Okay, but of course, we should, of course, do it right. So if we do it right with parentheses, then Jackson, what number did you get?
4.5.
4.5. Okay, so our final answer there is 4.5. And our units, of course, are going to be meters per second. All right, so good review problem, right? Now, this also leads into what I want to talk about, what you're going to need to know for tonight's homework problem. We did this using conservation of momentum. But you guys know that there's also a law called conservation of energy. So let's take a look. Let's see if energy is conserved like we think that it is. You guys realize I've got an offer outstanding where if you can break the laws of physics, then we can all go home and take the rest of the year off. Let's see if maybe we can do that. Okay, so what I want you to do now is I want you to take this same problem that we just did, and let's look at it from a conservation of energy standpoint. So everything is all happening at the same level here, so we don't need to worry about potential energy. The only energy that's going to be present here is kinetic energy. So I want you guys to calculate how much kinetic energy do we have before the crash occurs. So this guy here, he's not moving, so we don't even have to worry about him at all. The only guy who has any energy at all is this guy over here. All of his energy is kinetic. So again, I want you guys to type into the chat box, and this time I want everybody to do it, okay? Not just 3 or 4 of you. I want everybody to calculate how much kinetic energy does this do we have before the crash. Okay, so my picture here is so messy that I apologize for that, but let's see if that makes it a little easier. Okay, so what we have before the crash, only one object is moving, and the mass of that object is 3 kilograms. It's moving at a speed of 12 meters per second. Okay, so type into the chat box in a private message, how much energy do we have? I see one answer, but I need to see more. Okay, I'm starting to see more answers now, and good. The answers that I'm seeing are all the same number, so that's reassuring. Okay, so it looks like you guys are in agreement that the total energy before the crash is 216 joules. And if you're one of the few people who didn't get that, so remember that kinetic energy is 1/2 mv squared. So if m is 3 and v is 12, okay, type it in. And so we should get 216. That's how much energy we have before the crash. Okay, now let's compare that with how much energy we have after the crash, right? So we just got through calculating that the velocity of this mass is 4.5. So let's do it again. So let's do 1/2 mv squared, but m this time is the mangled mass, which is 3 plus 5. So m this time around is 8. And we just got through calculating that the velocity is 4.5, so stick it in there. And so type into the chat box, tell me how much energy do we have after the crash? So I see one answer. I see two answers. Okay, a couple of the answers that I'm seeing are different from the rest. The answer that I'm seeing most often is 81. Oh, but oh, boy, I'm seeing a lot of different answers. I better do this one myself here. So 1/2 times the mass, which is 8, times 4.5 squared. So yep, 81 is the answer I'm getting to. All right, so let's take a look at this and let's see what if there's something fishy here. Before the crash, we had 216 joules of energy. After the crash, we only have 81 joules of energy. Did we just break the laws of physics? Does that mean we can all go home? Which I realize is a crazy question, seeing as how we are all sitting in our homes right at this moment. Okay. What happened to the energy? So Calvin is saying that we didn't break the laws of physics. Right, Calvin, if you think that's the case, then tell me, where did the energy go? Ah, okay. So Taituan is saying that we're forgetting about the other types of energies. And Taituan is exactly right. Okay, the energy didn't disappear. We didn't break the laws of physics. Okay, think of it like this. Here is a popsicle stick. And let's say that I've got some object here. The object is coming along and it hits the popsicle stick. It bends the popsicle stick a little bit, but not very much. And then it comes to a stop. The popsicle stick acts like a spring. So it's going to spring back and it's going to end up pushing the thing. So this popsicle stick is acting exactly like a spring. So we got kinetic energy comes along. It flexes the popsicle stick. So all of our kinetic energy got converted into spring energy, or you can call it elastic energy. And then when the popsicle stick springs back, it sends the thing the other way. So we've recovered all of our kinetic energy. Okay, so this flexed popsicle stick has what we call spring energy, which falls under the category of mechanical because we can get it all back. What if I throw this thing so fast, so when it hits the popsicle stick, it's going so fast that it pushes it so much that the popsicle stick breaks. Okay, so clearly the popsicle stick is not going to spring back, so we're not going to get all of our energy back. So we had some kinetic energy before. When it hits the popsicle stick and breaks the popsicle stick, some of that kinetic energy went into breaking the popsicle stick. We had a bunch of bonds here, a bunch of chemical bonds. When we broke that popsicle stick, when we deformed the popsicle stick, energy had to be used up in order to deform the popsicle stick. Well, the exact same thing is happening here with our clay. Okay. Let me get a new picture here because this picture is getting too cluttered. All right, so when we had a ball of clay traveling along here with some velocity, and it hits this other ball of clay here, if the two of them stick together, then what happened is that the clay got deformed. So instead of having two round balls of clay, I now have a kind of a mushed ball here that is combined with another mushed ball here. So some deformation occurred. And that's exactly like if my popsicle stick got broken. It required energy to deform the clay. So energy didn't just mysteriously disappear. We know where it went. It went into deformation. All right. So this is a really important thing that I want you to remember, is that when you have a collision, there are different types of collisions that you could have. You could have a collision where they stick together. And we have a special name for that, which you need to know. We call that an inelastic collision. So if they stick together, we call that inelastic. Then there's the other kind that we can have where they bounce apart. Okay, so we call that kind of collision elastic. Okay, but it turns out that there's also an intermediate type. Okay, so we need to distinguish here. This one where they bounce apart, where they call it elastic, let's assume that they bounce apart and this is very important, there's no deformation and there's no other type of thing happening that steals away energy. And when I say other, I mean, like, for instance, let's suppose I have two objects, and when they hit each other, did you just hear something? You heard something, right? You heard sound. Sound is a form of energy. So if you hear two objects crash, well, some of the energy went into the sounds. Even if the objects didn't deform each other, if you heard something, then some energy, some of our kinetic energy is quote unquote lost. Now, I don't like to call it lost because we know where it went. It just got transformed into a form of energy that is kind of like heat, because once you get it into sound energy, you can't very easily get it back into usable mechanical energy. And speaking of heat, you know, when two objects hit, they probably are going to heat up. Okay, so you're going to have some thermal energy there as well. Okay, so if we look at the kinds of collisions that occur in the world, if they bounce apart and if no energy at all is lost to any non-mechanical form, you know, like heat or your sound or deformation, then we call that a perfectly elastic collision. So the intermediate kind of collision here, that would be one where they bounce apart. But some energy is, now I'm going to go ahead and write the word lost here, but I'm going to put it in parentheses because it's not really lost. We know where it went. It just went into a form of energy where we can't recover it. Okay. Sound, heat, deformation, something like that. Okay, so that type of energy, we call that a partially elastic collision. So as you can guess, very few collisions of the kind that we can normally experience, very few of them are really perfectly elastic collisions. And very few of them are perfectly inelastic collisions, although this one is actually not unheard of. I mean, in fact, you know, the more I think about it, it probably actually happens a lot. Anytime you have a collision where the two of them stick together, that is a perfectly inelastic collision. So if you have a bullet that comes and hits a piece of wood and it gets embedded in the wood, which by the way, you might have in your homework tonight, okay? If the bullet gets embedded in the wood, that's a perfectly elastic collision, okay? Anytime you have a collision where the two things hit and they bounce apart, that's an elastic collision, but the odds of it being perfectly elastic are pretty low. Most of the time, it's just going to be a partially elastic collision. Okay, so let's look at a couple things like you will see in the homework tonight. Let's go back and look at a whiteboard here. Okay, so let's say that we have a car driving down the road and we're in a helicopter above looking down. So here's the car. So it has a mass. We're going to call it M1, moving with a velocity V1. And here's another car. Has a mass M2, moving with a velocity V2. And doesn't have to be moving in a different direction, but let's assume that it is. Okay, so I see Calvin is asking, to be completely elastic, would the two objects have to bounce away without losing speed or momentum? The total momentum is always the same. And in fact, thank you for reminding me this. This is something that I should have said. Okay, back when we have these different types of collisions, momentum is always conserved. It doesn't matter if it's an inelastic collision or a perfectly elastic collision or a partially elastic collision. It doesn't matter. Momentum is always, always, always conserved. Okay. The thing that's not always conserved is mechanical energy. Now, total energy is always conserved. But if you just look at the mechanical energy, if you look at the kinetic energy and the potential energy, mechanical energy is only conserved if it's a perfectly elastic collision. Okay. If it's anything other than a perfectly elastic collision, then some mechanical energy will be quote unquote lost. Okay. Okay, so let's go back into this one again now. So we've got two cars that crash into each other. And so this is the before case. And now in the homework tonight, they're going to tell you what V1 is, what V2 is. They're going to tell you what M is. You're going to tell what M and M2 are. Okay, so let's assume that those are all known numbers. All right, and now afterwards, so let me switch to a different color ink here. So afterwards, let's assume that they're bouncing apart. So M2 is still the same mass. It didn't lose any mass during the collision. No bumpers fell off or anything like that. Okay. And so it's moving with some velocity now. Now I can't call both the velocities before and after V2 because they're probably going to be different. In fact, they will be different. So the velocity before, let's call that V2I, and the velocity after, let's call that V2F. And then same thing with mass number one. Okay, let's assume that it doesn't lose any mass. No bumpers fell off, no broken glass lying on the street. Okay, and so it's going to bounce off and it's going this way. And so let's call this one V1 final. And this first up here, let's call that V1 initial. So all of the numbers that are going to be given to you in the problem, and except V1 final and V2 final. So that's going to be your job, is to calculate what is V1 final, what is V2 final. Okay, so let's see how we would do that. Now, we know that momentum is always, always, always conserved. It doesn't matter whether it's an elastic collision or an inelastic collision. Momentum is always conserved. So let's go ahead and just write sigma p before the crash as equals sigma p after the crash. So before the crash, we got M1 V1 initial plus M2 V2 initial. And that has to equal the momentum after the crash, which is M1 V1 final plus M2, oh, yeah, I've got it right, plus M2 V2 final. All right, and let me circle the unknowns here. So you can see we've got two unknowns and only one equation. Not going to do the job for us. If you got two unknowns, you need two equations. Where are you going to get the other equation from? Well, the other equation is going to come from conservation of energy. So what we're going to do is we're going to say sigma E before the crash has to equal sigma E after the crash. Now, a lot of students are tempted to say, well, okay, sigma E, that's kinetic energy plus potential energy. So kinetic energy before, potential energy before, and they're going to say, and they're going to be tempted to say, well, that has to equal the energy afterwards. So kinetic energy afterwards plus potential energy afterwards. But do you see the mistake that they're making? If they stop right here, they've got a big problem because they are forgetting about the other forms of energy. They're forgetting about the fact that when the crash occurs, you know, there's going to be sound energy given off. If the car's bumpers are crumpled, then there's going to be some deformation energy that takes place. Okay, and so if you don't write in plus other, then you have no hope of getting the answer right. You have to account for this other types of energy. Now you might say, what about other before? Shouldn't we say plus other over on the right side? To which I would say, yeah, except that, I mean, before the crash occurs, you know, there's been no deformation, there's not going to be any heating, there's not going to be any sound. So before, we don't need to worry about other before. But after the crash, we very definitely need to worry about other, very important. Okay, so what have we got? Well, in this case, everything is occurring at ground level. So that means with potential energy doesn't even enter into the equation really. The only thing we have here is kinetic energy. So that's going to be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. That has to equal 1/2 m1 v1 final squared plus, I'm running out of room here, so we'll write down underneath, plus 1/2 m2 v2 final squared plus other. Do not forget plus other. Okay, so again, I'm gonna circle the variables that we don't know. So here's our v1 final, here's our v2 final, but we've also got this other. So we now have 3 unknowns and only 2 equations. Okay, so it looks hopeless. Well, the way that we're going to do this in the homework tonight is that they'll have to tell you one of these. So maybe what they'll do is they'll tell you what V1 final is and ask you to calculate V2 final and other. Or maybe what they'll do is they'll tell you what other is. Okay, and that one's probably the more likely. So maybe what they'll do is they will tell you, they'll just pick some number. Let's say that 3,920 joules of energy is quote unquote lost. They're going to say, okay, that's how much energy got converted into thermal and deformation and whatever. Okay, so we'll know what the other is. Okay, so we will in fact have 2 equations, 2 unknowns. Okay, or another thing that they might do is they might tell you that it's a perfectly elastic collision. Okay, so if they use that phrase, if they say that it's a perfectly elastic collision, what does that mean about this other term? Somebody unmute yourself or type in the chat box, tell me. If in the problem statement you see the words perfectly elastic, what does that tell you about other? Okay, okay, so I see somebody just sent me a private message. Say it means that it's 0. Okay, that's the definition of a perfectly elastic collision. It means that no mechanical energy is converted into non-mechanical energy. Okay, so if they say it's perfectly elastic, then you know that other is 0. Okay, so tell you what, let's do an example like that. Let's assume that we do have a perfectly elastic collision, right? So if that's the case, what have we got here? Well, we've got M1 V1 initial plus M2 V2 initial has to equal M1 V1 final plus M2 V2 final. So that comes from conservation of momentum. And then from conservation of energy, we've got 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared has to equal 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And then I'm going to go ahead and write plus other, just because I want you to get in the habit of thinking about it. But if the problem says that it's perfectly elastic, then that means that other equals 0. Okay, so what do we got? 2 equations, 2 unknowns. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Well, this is a messy math problem. This is clearly the kind of problem that I would only give to the honors physics class. I would not give a problem like this to the regular physics class. You can do this. It's not easy, but you can do it. How would you do it? Well, when you got 2 equations, 2 unknowns, you know, one way to do it is elimination, but elimination isn't going to work in this case, because if you look at the variables that we don't know, okay, these are the variables that we're trying to solve for. You see here, the variable we're trying to solve for is squared. If you ever have a case where you got a variable that's squared or square rooted or a sine or cosine, you cannot use the elimination method. Okay, you can only do the elimination method if it's a linear equation. Same thing with matrix. Those of you that know how to use matrix math, okay, matrix math only works if they're linear equations. So we're going to have to do substitution. That's okay. It's not that bad. So tell you what, let's take this equation up on the top because that's the simplest one. And let's pick one of the variables. I don't really care which one. Let's pick this variable right here. So we're going to solve for V2. All right, so how are we going to do that? Well, we're going to take this guy and we're going to move him over to the other side. And so let's put it down here and see what we get. So we're going to get M1 V1 initial plus M2 V2 initial. Now we've moved this guy over here, so he's going to come in with a minus sign, minus M1 V1 final. Okay, so that equals this, but we want to solve for V2 final, so we're going to have to divide everything by M2, and that will tell us what is V2 final. Okay. Now we look at the other equation, we see we got a V2 final right here. So wherever we see a V2 final, we just take this thing that we know V2 final is equal to, and we plug it into here. And then we've got one equation, one unknown. So you guys know how to solve one equation, one unknown, right? Now, I will admit this is a really, really, really messy equation. Now, it is possible. If you guys work at this really, really hard, it is possible that you can solve this the way that your math teacher would want you to solve it. But it's not worth the effort. There's an easier way. Remember, we talked about this before. We talked about a way that your math teacher doesn't necessarily like too much, but I think it's a great way to solve it. As long as you can get it down to one equation, one unknown, it doesn't matter how messy that equation is. You can solve it using this technique that we used before. Somebody unmute yourself or type in the chat box. What is the method that we learned for solving messy equations as long as we can get it down to one equation, one unknown? What's the method that'll work? Say it louder.
Elimination?
Say it again.
Is it elimination or no?
Well, that's what we just did. That's how we get it down to one equation, one unknown. But once we get it down there, okay. So I see people are suggesting quadratics, but that's the way that your math teacher would want you to do it. And it could be done. You can take this really messy equation and you can put it into a quadratic equation. It can be done that way, but there's a much easier way to do it. Desmos, yes, Mia is exactly right. Desmos is the way to do it. Okay, so let's remind ourselves how we did this before. What we'd had before was we had two really messy equations, and using substitution, we got it down to one even messier equation. So what we have is we have some super messy equation where we've got an x and maybe we've got an x squared, maybe we've got an x cubed, maybe we've got a square root of x. We got it, but it's all the same variables, all the same x. And then that's equal to some other really messy equation. And again, we got an x and maybe we got a sine of x, who knows? So we've got one variable in there, but it appears multiple places and it appears in a really messy way. So what we did before in order to solve this equation was we rearranged the equation. So we bring it over to the other side here. And so what we get then is we get 0 equals some really super messy equation that's got an x and it's got a sine x and it's got a square root of x and it's got an x to the 5th and ugh, it's just horrible, okay? But it's the same x. So it's just one equation, one unknown. So once we get it in this form, then we can say, well, what if we, instead of being 0 equals, what if we call it y equals this? And we put it into Desmos and we let Desmos graph it. And so Desmos is going to graph it and it's going to get some really weird thing that's going to, maybe look like this. And so that's what we get out of Desmos. And then we look back and we say, well, when we put it in Desmos, we put it in as y equals, but we weren't really interested in y equals. We were really interested in 0 equals. So all we have to do is look at this graph that we got from Desmos and look to see where does our thing equal 0. And wherever it equals 0, that is the answer that we're looking for. Okay, so that's what I want you guys to do in tonight's homework. Okay, you're going to get a really, really messy equation. Actually, you're going to get two really messy equations. Okay, and so you're going to use elimination and get it down to be one equation, one unknown. And you don't care if it's messy because Desmos can solve any equation for you. Doesn't matter how messy it is. Okay, now one thing that might happen is when you put it into Desmos, you might get something that looks like this, where you have not just one solution, but two solutions. That's okay. Don't worry about that. Now, if we were trying to solve for time and we get one of our solutions is a negative number, then we say, oh, okay, well, that's just what we call an extraneous solution. I mean, if time could be negative, it would work, but we know the time can't be negative. So we just say, okay, we'll just ignore that. And so this is our answer, okay? But that's not what you're going to do in tonight's homework. In tonight's homework, it's not going to be time. It's going to be velocity. It's going to be like V1 final is what we're going to be looking for. Can velocity be negative? Answer, yes. Okay, so this negative answer here, we better not go discarding it because that might in fact be the right answer. Okay, so let me tell you how it's going to work. When you do this tonight, you are going to find that you will get two answers. Whoops, I hate it when I do that. Let me try this again. Okay, so you are going to find that you will get two answers when you do it tonight. One of the answers will be the same as your original V1. So let's suppose it's this one here, okay? This one will be the same as V1 initial, okay? So V1 final, V1 initial, Desmos is going to give you an answer. You mean the word the same. So you're going to look at that and you say, well, that one's obviously not it, okay? Because V1 initial and V1 final in the real world, can't be the same. Mathematically, it might work out, but physically, we know that it can't be right. So we'll say, okay, well, we'll ignore that one and this other one here. They must be the right answer. Okay. All right. So with that being said, well, first off, let me just ask, are there any questions about what I just did? Does that make sense to you? So tonight, the physics is not really going to be that difficult. The tricky part is going to be is the math. Now, most of the problems in tonight's homework, you are not going to have to solve using Desmos. Most of the problems tonight, the book is going to give you enough information that you'll be able to just plug them into the equation and you won't have to worry about using Desmos. But one of them you will. Okay, so in fact, let's go ahead and let's look at my Canvas page here. Let me go ahead and click on homework 11B. That's the one that is tonight. And okay, all right, so what you can see here is, oops, excuse me, hang on a sec. Okay, all right. So what I've done is I've given you, most of your problems are going to be problems out of the book. And these problems are going to be relatively easy. You are not going to have to use Desmos to solve any of those problems. But I've also given you an extra credit problem, which I made up. Okay. This is a problem where you will need to use Desmos to solve this one. Or, by the way, let me just mention one thing real quick. You guys realize that you don't have to use Desmos. You've all got graphing calculators, or at least you should. You should all have graphing calculators. You can do it on your graphing calculator the same as you can do on Desmos. Just put it into your graphing calculator, graph it there, see where does it equal 0, bingo. Okay, Desmos is easier to use. So that's the one I would recommend, but you can use your graphing calculator if you want. Okay, so let's go back to here. All right, so this extra credit problem, which by the way is extra credit, okay? If you think that using Desmos is more trouble than you want to do, okay, fine, it's extra credit, okay? But I highly recommend that everybody do this, okay? Now notice I've told you right here, I say that the collision is totally elastic. So that means that no energy is lost. to deformation or sound or anything like that. So you can assume that kinetic energy after is equal to kinetic energy before. That only works if it's a totally elastic collision, but this is a totally elastic collision. Okay. All right, well, I think we are done. If you don't have any questions, go ahead and type into the chat box, you say bye, and I'll see you later. If you do have a question here, what I'll do is I'll go ahead and turn off the recording so you can ask your question without embarrassment.